Welcome to Brain Vision.
All right, so in this problem we have a length of wire of length d here that's carrying a current I, and we want to find in part A what the magnetic field will be at point P, which is a distance r away from the middle of the wire here. So we'll use Biot-Savart for this. So we set that up like B equals mu naught I over 4 pi, and the integral of dl, and I'm going to write this as cross r vector and then over r vector cubed. So sometimes you could write this just as a unit vector, but this will be a little easier just working with the full vector here. So this is our equation. So let's start filling in some of the variables and coordinates we're going to use here. So I'll kind of mark in our arbitrary little spot dl here. So let's say this is our little dl. So that's dl there. And that means that this vector here would be vector r, so the distance from dl to point P. And we'll set up our coordinates here. So I'm going to call this middle part, we'll call that y equals 0. And so that would put this, the top part, as negative d over 2, and the bottom as d over 2. I guess you could switch those if you wanted upwards to be positive here, but it shouldn't really make a difference at all. Okay, so next then we can start filling in some of this dl cross r here. So we're going to have mu naught I over 4 pi. And then our integral, well, our integral we now know should run the full length of this wire. So that's going to be from d over 2 to negative d over 2. And then I guess I've been calling this the y direction now. So instead of dl, we'll say dy now. So we have dy cross our r vector. And to do this cross product, it'll be easier if we write the r vector in terms of its components, since that can make doing cross products easy, since parallel ones will just be 0. So it looks like then at this arbitrary point, our r vector, we could just write as whatever y positions it's at, so it has some vertical height. So yj hat, and then plus ri hat. So we're just saying it has this much vertical component and this much horizontal component. And then we have this over r cubed. So by Pythagorean theorem here, r should just be the square root of big R squared plus y squared. So then we'd want this to the cubed. So now when we look at this cross product, because we've written it as components, it'll be a little bit easier. So dy is in the j hat direction. So then we can see pretty easily dy cross y, both of them are in the j hat direction. So the angle between them is 0, and so the cross product is 0 between those two. So the only thing that's going to give us a non-zero term will be dy cross r. And so something in the j hat direction crossed with something in the I hat direction should give us something in the negative k hat direction. So we can just pull all that out right now. So we'll say we have mu naught I over 4 pi. And then we'd have this r too, which is a constant, so we can pull that out of the integral as well. So then we have times negative r k hat. And now we have our integral d over 2, negative d over 2. And so it looks like we'll just be left with dy in the numerator. And now we'll have divided by, maybe I'll write this a little more cleanly here, r squared plus y squared to the 3/2. And so now this is a relatively simple integral that we can just evaluate. So you can look this up in a table. And we'll get, we still have all of this. And now this integral should evaluate to, looks like we'll have y over r squared times r squared plus y squared to the 1/2. And we evaluate that from d over 2 to negative d over 2. And so now we just plug in those limits of integration, keep all of these constants out front, and so I'll do the subtraction for you here, but we should end up then with negative mu naught I over 2 pi r, and then valuing that integral, then we get d over 4r squared plus d squared to the 1/2. And then remember, this is all in the k hat direction, and we have the negative sign out front. So to the negative 1/2 down there. So there we go. So that is the magnetic field at point P. And then part B asks us to check if this reduces to what we found in example 11. So in that example, we were seeing what happens if D goes to infinity. So if we had an infinitely long wire. So looking at this, this second term in the parentheses here, if we had D going to infinity, well, this 4r squared in the denominator doesn't really matter. So we just have D over D squared to the 1/2. So this is just going to become D over D, or 1. So this whole term just converges to 1 as D approaches infinity. And so then we'd be left with just negative mu naught I over 2 pi r in the k hat direction, which is exactly what we found in example 11, or what we'd find using any number of methods for the magnetic field from an infinitely long wire at a distance r away.